Thank you, Michelle. Thank you for the introduction. It's a pleasure to be here and to give you a short journey, a short introduction into gravity, magnetism, and space physics. There's a lot to say about these topics, and therefore I will immediately start with some pretty big disclaimers. So what I will basically not talk about here today. So I do not want to turn this presentation into a physics lecture. Absolutely not. It's also impossible to cover all these topics that are vast and have been driving the development in many areas of science, actually for centuries, in just 40 minutes of presentation. So this is one thing I like to share. And also, what I will not talk about is gravitation. Gravitation is something different from gravity. So gravitation is how, let's say, everything in the universe communicates with everything at the let's say atomic or subatomic scale. I will also not talk about, let's say, the intrinsic issue of exactly how magnetism works inside of atoms, nor will I talk about the very complex equations that basically drive and govern the dynamics of everything that is going on in the space around Earth, which is, by the way, not empty at all, as I will show in a short while. I will not talk about any of these things. I don't even claim that I understand all of these things in very detail, even though I've been studying gravity for 20 years, magnetism, I think, for 10 or 15, and space physics for a good part of a decade as well. So these are very, very intricate issues. But what I will talk about is a little bit why we send missions into space to explore gravity, to explore magnetism, and also the phenomena that occur in the space around Earth and how Earth actually interacts with the sun and with the space environment. And above all, what I'd like to do is to show some examples about what we learn from this type of missions. So what you will see here is a practical use of space as an activity that we undertake to gain knowledge for humanity and mankind, I mean, for the benefit of everyone, and how we do that through, let's say, the development of cutting-edge technologies, in particular in the instrument, but certainly also in the satellites that we, as the European Space Agency, launch. But before I come to any of these topics, I'd like to reflect a little bit with you on what actually is a mission. So it might sound a bit strange to you, perhaps, that me, as being responsible for mission operations, actually ask myself what a mission is. Shouldn't the guy already know that? But I took a look in the dictionary when I was preparing for this meeting to see what the dictionary says about what a mission is. And this is what I found in the Oxford Dictionary. And it talks about the important assignment that is given to a person or to a group of people. It also talks in some cases about religious vocation or calling. I will not go as far as claiming that sending a space mission or a mission into space is a religious thing, although it sometimes can be close to that. But what I really care about in this definition is that we are talking here about a strongly felt aim, ambition, or a calling. Because nowhere in this definition does the dictionary talk about the vehicle that takes us there. It doesn't talk about the satellite. It doesn't talk about an instrument. It talks about the purpose. And this, I think, is something that we need to keep in mind when we talk about what our space missions, as we call them, actually are setting out to do and why we are doing it and what we actually try to achieve from it. So I give you an example of what is a perfectly legitimate mission. I hope you can see it here. This is an extract, a very, very famous extract from a 1980s movie called The Blues Brothers, where these two gentlemen, Jake and L. Blues, they were on a clear mission to save an orphanage. And they were saving an orphanage because they cared about the kids. And although the mission that they executed was not, let's say, risk-free, they actually were on a mission. Now, what we try to do at the European Space Agency is to try to achieve our mission goals in a pan-European way with our partners, with our stakeholders, and with partner agencies and the scientific community in a way that doesn't lead to this kind of havoc, but definitely gets to the result that we have. So the key point here that I'm trying to bring across is that the mission is really the end goal of what we're trying to do. And the facilities that we use, called satellites or instruments, actually, to some extent, are tools. They are highly sophisticated tools, but the end goal is usually the knowledge that we gain. Now, having said that as an introduction, I'd like to talk a little bit first about gravity. So we have, you see here, three aspects of gravity. One is apple tree, where, as the legend says, Isaac Newton, he was sitting under his apple tree and thinking about the physics that were at play when the apples were falling. We see here also an evolution in the understanding of the Earth, let's say from the upper left down to the lower right, where as we start to gain understanding of the gravity field that is an intrinsic property of our home planet, grows as we develop more sophisticated technologies to actually understand it. And we see on the satellite in here, which is the Gravity Field and Steady State Ocean Circulation Explorer, also mentioned by Jorge Fauste earlier today, which was our agency's most sophisticated tool looking into the exploration of these phenomena. Now, you say gravity, but gravity isn't that a constant. That's what we learn in school. So the famous 9.8 meter per second square, or the famous G-force, isn't that all there is to it? Well, you might think so, but in fact, there is a lot more that comes into play here when we look at it in finer detail. So if you look at the figure here in particular on the bottom, we see the 8 first significant digits of G. And in an average sense, this is an average figure for the planet, where you see that the 9.8 meter per second square basically reflect the sphere. Then the third digit, the 0, then that takes into account the fact that the Earth is not entirely spherical. It is in fact elliptical, ellipsoidal, and it is also rotating. And to that order, the Earth actually takes in a shape which is governed by what is called hydrostatic equilibrium. Is what you get when you take a balloon and you rotate it, essentially. So it's taken into account the fact that the Earth is a liquid, although we don't all think so. It's a planet, a rigid planet that we all live on. But geophysically speaking, the Earth is actually a liquid. And then as you go on further to the right in this figure, you see various other phenomena that as you go to smaller fractions of G, you see other factors that play a role and then are actually measurable if you are having an instrument in space and on ground that is good enough to measure gravity all over the place. So for example, mountains are in the 4th digit. Ocean trenches are also in the 4th digit. The variation in the internal mass distribution, for example, due to supervolcanoes or mantle convection, things like this, are coming in the 5th digit, all the way out to tides. And then when you go into the 8th significant digit, you will start to see that the first human-built infrastructure starts to play a role in this figure of G. So you can see it coming that if you're able to measure gravity, you're able to understand the mass distribution of the planet in a better and better way, and you can use that to understand the science about what is going on, but certainly also to some extent to make use of that for all kinds of understanding of other processes that depend on information about the home planet in order to be fully understood. So that's first point. Then how do you actually measure gravity? It's not simple at all. Because if you think about it, space around us, everybody says it's a non-gravitational environment or zero gravity environment. But in fact, one of, let's say, Isaac Newton's brilliant ideas was that, in fact, in space, it's not zero gravity. The fact that you feel weightless is because you're actually moving, and the centripetal force is equaling the gravitational attraction by planet Earth. So even up in space, it's not zero gravity. There's plenty of gravity. In fact, it's almost the same as on ground if you are not too far away. But the fact that you are in orbit around this planet basically exerts a force on you that goes in the opposite direction, and therefore gives you the feeling that you will be as in free fall in that satellite or spacecraft that you would travel in. So that means that if you will put a balance, or what's called here a weightometer, inside of a satellite there, you will actually measure nothing. So you cannot just go there with a balance or something similar to that in space and measure gravity. Now, what if I don't have, and here comes the trick, what if I don't have one balance, but I have two balances? What then changes? Well, if you first step on one balance and you measure gravity, you can see a value here with a good number of digits, obviously, because you need a very, very precise scale to be able to do this. Then you can measure by moving, let's say, half a meter, and you measure a slightly different value if your instrument is precise enough. And then the difference between those two measurements, they are actually a measure for the variation in gravity. And this is, if you go back to the picture of Isaac Newton, if you put not one balance in the center of mass of your spacecraft or your space vehicle, but two balances or two scales in the spacecraft, this difference will actually not be zero. And because at those locations of where the scales are, the centripetal acceleration will not fully cancel the measurement by the scale. And this was something that Isaac Newton did not discuss. So there are ways of basically getting information from differential, that means difference measurements in space, provided, of course, that your instrument is extremely precise. And this is where the satellite called GOCHA, Gravity Field and Steady State Ocean Circulation Explorer, comes into place, into the picture. So this is, at least, although I must confess that I am slightly biased, this is a Ferrari of satellites. Not only was it red, painted red, but it was also equipped with a super sophisticated engine that allowed it to fly at a super low altitude, basically cutting through the upper layers of the Earth's atmosphere. And it had this slender shape, aerodynamic shape, and on top of that, it also had winglets at the back that made sure that the satellite was aerodynamically stable. And this is something that you don't see very often when you talk about satellites, because most satellites are not affected at all by the remnants of the atmosphere, because they tend to fly much higher. This is a feature only for satellites, and there are not many that fly at a very low altitude. Now, just to get you a feeling of the numbers that you need in order to be able to do such a thing, and also perhaps to give you some respect for the technology that is at play here. I mean, imagine that you take a super tanker, an oil tanker that carries oil from one continent to the next. Imagine that you have a super tanker that has a displacement of about 100,000 metric tons. Now imagine that you are out on a winter night with the super tanker over the ocean, and a snowflake, which has a mass of about 5 milligrams, is in the air. Now, the supertanker acceleration due to this single snowflake falling onto the deck of the ship basically equals this number that you see here. That is a 2 with 11 zeros in front of it. And this is exactly the smallest acceleration that was measured by the GOCHA satellite and the sensors on board. This is the measure. So by principle, building these two scales that are able to make a difference measurements of gravity, though the principle is very simple, the execution of it is extremely complex. Now, so basically what we are talking about here is what I call nanotechnology on steroids. And what we do then with the spacecraft, I try to see, I hope you can see.
The GOCHA gradiometer consists of 3 pairs of identical ultra-sensitive accelerometers mounted on 3 mutually orthogonal arms. One of the arms is aligned with the satellite's trajectory, one pointing towards the center of the Earth, and the third is perpendicular to the other two. This allows the simultaneous measurement of 6 independent but complementary components of the gravity field.
Good. So what I wanted to show here, I hope you could catch that, is that with these 3 pairs of differential scales inside of a satellite that is then orbiting around the Earth and the Earth rotating underneath this spacecraft, you're able to make a map of the gravity field. And this is basically how this mission was executed from 2009 to 2013. Now, why do we do this? Why are we keen and interested on this? Well, first of all, we all know that the gravity is a reflection of the mass distribution inside of the planet, and so it means that the gravity field, as such, is a mirror of all the interior processes that go on inside of the planet. You know, from the core to the mantle, but certainly also in the crust. And so understanding the gravity field means that you have a way to look inside of the planet. But perhaps even as important as that is that we need a good physical reference surface for all of the processes that occur on the surface of the planet. So everything that is linked to land, ice, ocean, atmosphere, that needs sort of a real physical reference and not a geometrical one that is measured with a ruler, basically requires gravity field information. And this is the concept of what's called the geoid. So the geoid is it's called an equipotential surface, but basically what it means is that if you would have an ocean that is completely at rest, so without wind stress and waves and things like this, this ocean would then have the shape of the geoid because it will always be perpendicular to the local gravity vector. So this then is allowing us to understand if something that is higher up than something else, because if something is higher up, then water would flow or liquid would flow from that higher point down to a lower point. So it's a really excellent and very, very useful in the earth sciences surface for all the physical processes that take place. So everything that we do linked to climate change, sea level rise, the water cycle, height systems, the melting of the ice, as you heard about, I'm sure, being a big problem because it causes also sea level rise in part, but also groundwater flow. All these things are then measured with respect to the geoid and not with respect to some of the more artificial height systems that exist in this world. So this is key, very good to remember. And this is actually how this geoid, this equipotential surface or the physical shape of the Earth looks like. It's just one side of it. This is, you have Africa on your left, you have Southeast Asia on your right, and you have India more or less in the middle of this picture. And this equal energy surface, equal height surface, if you will, if you would be on it, if you would sit on it, and you would travel by ship from the Horn of Africa to the southeast of Asia, you would actually, with respect to the center of Earth, go down into a hole which is about 110 meters deep. Although gravitationally speaking, you would be on exactly the same height. So this is, of course, a reflection of the fact that underneath the Indian Ocean, there is a mass deficit, and most of that is now residing in what we all know as the Himalayas, because that mass has to go somewhere. And doing this with the satellite, we were able to hit also the news. These are two newspaper headlines from a few years back when we presented this as an outcome of the mission, and two of the main German newspapers actually published this on their front page because they found this extremely interesting to understand and to see how actually such a thing that resides from gravity actually has practical implications for all of us. As I said, we can use this to understand the density variation inside of the Earth. Here are two cross sections of that. One is basically with the Andes Mountain, and the other one is, again, the example of the Himalayas. And doing this with this satellite, we were able to produce the most precise crustal maps ever. Crustal map means the thickness and composition of the crust. And then once you have that, you can actually use it for even bigger, let's say, more societal activities. you can invert the crustal structure for heat flow. And this is done here for the Arab Peninsula, basically Saudi Arabia, where you can then use the heat flow map to invert for hydrocarbon maturity, and you can look for areas where you are likely to find oil or also gas. And in the end, you can look at the change of these maps from before we had this satellite and after this satellite. And you see that the understanding of where the hydrocarbons are located changes after having flown this satellite. And something very similar can be said for geothermal energy sources, which is one of the most unutilized or underutilized energy sources that we have on this planet. Here is another example of what you can do with this geoid. So I said to you that the geoid is a reference surface that more or less coincides with the ocean at rest. And then everything that is not the ocean at rest will then occur as a difference with respect to that surface. So here we show what is called the surface currents all over the ocean, where you take several decades of satellite altimetry, so these are radar height measurements of the true ocean surface, and you subtract this super precise gravity field model from the Gocha spacecraft, and you see you can invert that for what's called the currents. And you can see currents all over the ocean. You see the Gulf Stream, we can see the Kuroshio, which is the main current off to the coast of Japan, and also the big Agula system, which is at the tip of Africa and then towards the Antarctic continent, basically. And on top of that, we see also signals like the El Nino and La Nina that I'm sure that you've all heard about, that are more or less occurring in the equatorial region. All of these things are then used by experts to estimate how much water is actually circulating in the ocean, and with it, how much heat and energy is going from one place to the other as input to the climate discussion. So what I'm trying to say with this is that through the measurement of mass and gravity, because gravity actually equals mass, we can then look into things like drought. We can look into where the water in the ground is going, because if the water is no longer there and it's evaporated, the mass is less, and we will see that in the gravity measurements. We can use the same thing for looking at differences in the gravity field before and after an earthquake. We can look at things like sea level rise and so on. All of these things show up in the gravity field. So again, if you have a super precise gravity meter or a scale, if you will, that you can fly in space, you will be able to monitor these things, and is one of the most important climate observations that that can be done, because we all know that water is one of the more well, it's the most valuable how do you call it, resource that we have. It's more valuable than gold and the oil, and this water is going to be the oil of the future, at least fresh water. Yeah? So these are very important reasons why we measure and build this super technology satellite, giving us, let's say, all these informations about the gravity field. I will move on now to magnetism and space physics. This is the second part of my talk, and wanted to start a little bit to introduce to you what is called the outer core. You may know that the Earth is built of an inner core, an outer core, mantle, crust, and so on. And what is not known to everybody is that well, that this outer core is very special. I'm sure you know that today it is believed and understood by almost everybody who are at least specialized in this field, that the main magnetic field, or the main part of the Earth's magnetic field, is generated in a geodynamo, in a dynamo that that is operating in the outer core of the planet. And this has been proven by also by simulations, and it's very well sustained by all the observations that are being made. And this outer core, it generates about 98% of the total magnetic field. And what is then happening in this outer core is that we see fluid motion at a few tens of kilometers per year. So it's not very fast, but geophysically speaking, it is extremely fast compared to, for example, the motions of the tectonic plates or things like that, or mountain building, or convection in the mantle, the other main geophysical processes, which are centimeters per year or millimeters per year. He talked about several tens of kilometers per year. And in this outer core, then what's physically happening is that about 1 million, I repeat, 1 million kilograms of iron freeze every second onto the inner core. So in this process, there is convection that is carrying a lot of this heat out of the core, and this gives the energy to the geodynamo and keeps this process running. Now, this geodynamo is essential for our planet because it gives us the shield that is protecting us from harmful radiation from space. And not only us people, but also the critical infrastructure that we nowadays have in space around us. For example, think about satellites that we use for navigation, for telecommunication, for television, for disaster monitoring, for many, many other things. And you will see another example in this the talk just after mine. So we should be very, very grateful that we have this magnetic field, because without it, life as we know it would not be possible on this planet. And also it's kind of a curious fact that not all the planets do have such a magnetic field. Mars, for example, does not have it, and that is believed to be one of the reasons why Mars no longer has let's say, very strong atmosphere, that it was actually stripped of its atmosphere. Yeah, and Venus, although it doesn't have a magnetic field, is an oddity, because even though it doesn't have a magnetic field, it still has a very, very thick atmosphere. So there's plenty still to be learned about the planets also here. And all of this, actually, all the studies and everything that was done in order to understand the magnetic field was then triggering Albert Einstein, who this needs no further introduction, to say that the Earth's magnetic field is one of the greatest unsolved mysteries of physics. And that, of course, we have learned a lot since Einstein, but we don't know everything about the magnetic field. And so we decided to launch a space mission also for this. And what we then do with this space mission is that we measure the magnetic field at the satellite altitude, a few hundred kilometers. We then convert that into models about the magnetic field. This is what we see here. By the way, the unit of magnetism is actually Tesla, or nanotesla, after Nikola Tesla, who started to use it. And you can basically see here that the magnetic field is not the same all around the planet. You can see the areas in red where the magnetic field is stronger relative to the areas where it is blue. And the dynamics of this is actually not small, it's more than a factor 3. And this big area in blue that you see more or less in the middle of this picture is what is commonly referred to as the South Atlantic Anomaly, which is a bit bigger than the South Atlantic nowadays. But this is an area which is where the magnetic shield protecting us is shielding us much less than over the rest of the planet. And this is therefore also an area where much more radiation enters into the upper atmosphere, and also an area where satellites tend to have technical problems. We can then go further and we can convert that information into information deeper into the planet. And this is what we see here, going 3,000 kilometers below the surface. And then you see that the magnetic field there at the boundary of the outer core is even more irregular. And you can see these big differences in the red positives and the blue is not negatives, but weaker magnetic fields. And these are reflections of the features of the dynamo inside of the core, where the flow is fast, where the flow is slow or relatively slower, and so on. And these are things that change with time because the magnetic field is by far not constant. A little bit more detail here, and then I will go to the conclusions on this. What you see here on your left is basically an attempt by modelers who use our data to show exactly what is going on inside of the outer core. So in yellow, you see the magnetic field lines inside of the outer core. And in red and in blue, we see the depicted motion of the fluid following simulations. So you see that there is nothing that is really always the same, or there's not the same pattern everywhere. And this is exactly what gives rise to these red and the blue areas with different magnetic field strength that you've seen before. And because the liquid is moving with a few tens of kilometers per year, these features are also moving. So the take-home message from all of this is that the magnetic field is far from constant. It is actually changing very fast. In the past 200 years, apart from the motion of the magnetic poles that I will mention in a second, we have seen a global decline in the strength of the magnetic field of somewhere in the range of 9 to 10%. So if you think about it, if someone would say that the atmosphere would have become 9 or 10% thinner in 200 years, it would have been a big cry, of course. The magnetic field, which is our main protector from harmful radiation from space, has actually seen such a big change. I'm not saying this because I want you all to be worried, but it is a fact that the magnetic field is not only changing, but it also tends to flip, and has done that on several occasions throughout the history. And so we are monitoring this, and it's an important endeavor for the space agencies to actually continue to measure the evolution of the Earth magnetic field. Now, why is magnetism and space physics related? Well, here I zoom out and do no longer focus only on the Earth. You see basically a picture of the sun and everything that the sun is sending towards Earth. You see a picture of the Earth, which has its magnetic shield, and then that's seen here with the magnetosphere that you see in blue. And of course, what we already talked about, the core and everything that's happening inside of the planet. So when you look at magnetism from this perspective, it is obvious that some of it is linked to the planet itself and the dynamo that is going on, but other parts are also due to what's coming towards us from the sun. So there are sun-driven aspects of it, and there are Earth geophysical aspects to it. And these things, they change also not only in spatial scale, but also in temporal scale. So in order to actually understand what's going on inside of the planet, we also need to understand what is coming towards us from the sun, how that is changing in time, and so on. So it's very much true in this business of and necessary magnetism. And I don't want to go into to show you that space physics is extremely complex. This is a picture that tries to show basically all of the things that are going on in the space around us, how we are fed or feeding this process with energy coming from the sun, with particles coming from the sun and from outer space, and how this thing is also fed from below, everything that is coming, let's say, or is happening inside of Earth itself. So, and this is then affecting not only the charged particles or the electrical particles that are flying around, but also the neutral atmosphere. And I do have a nice animation which shows what happens when there is a storm in space. So geomagnetic storm following a big burst of activity on the sun that is sending a lot of solar wind, let's say, towards the Earth, and how the Earth atmosphere responds to that. It's not suitable for presentation in WebEx, but you can see that this enormous heating event basically expands the entire Earth's atmosphere and basically moves most of Earth's air masses all around the planet. It's pretty impressive to see, actually. So in order to understand this, we, the European Space Agency, we then built a mission, which is called SWARM, which is then trying to combine all of these things, to combine the understanding of the core and everything that's happening inside of the planet with the geophysical aspect, and then looking into everything, all these phenomena you see here, like from the core all the way out to the magnetosphere. And the key point here, I don't want to bother you with the detail here, is that you need to be more than one, because it's only with having more points of observation and more satellites that we are able to disentangle all of these phenomena. As you see here, one pair of satellites is in darkness, whereas another satellite is in daylight. And in daylight, you are very much affected by the processes that are coming from the sun, whereas at nighttime, these processes are calming down, and basically what you are driven by are the geophysical aspect. So by looking at the same phenomena at different local time, at nighttime and daytime, we are going to be able to build a better picture of what's going on and how to let's say, understand what is coming towards us from the sun and what is really governed by the Earth itself. And to give you some result of what we have been able to find out here, I call this slide the sprint of the magnetic North Pole. On your left here, you see an evolution of the location of the magnetic North Pole since 1831. And you see that in about 150 years, from 153 years, from 1831 to 1984, there was a certain pretty stable motion of the location of the magnetic pole. Then in the next 21 years, it basically covered the same distance as it had done in the previous 153 years. And then again, in the 14 years that follow after that, it went again, covered the same kind of distance. So it means that the magnetic pole is sprinting. And what we were trying to find out with the satellite is why that is the case. And that's what is located on the right side of this image, where you could see the magnetic field at the boundary of the outer core, as it looked in 1999, and how it had changed between 1999 and 2019. So this is 20 years of time span that is covered. And this is the reason then why the magnetic North Pole location has changed, is because these blobs in the magnetic field and in the convection, if you will, that is going on in the geodynamo has actually moved. So it's a result of the physical movement of the liquid iron in these regions. And the funny thing is that we do not observe anything similar at the magnetic South Pole, which is extremely stable. And to understand the geophysics of that and if that is going to remain like this in the coming hundreds of years, of course, remains to be seen. But these are typical things that we are able to map and understand with our satellites. Then another aspect that you probably know about the magnetic field is that the crust is magnetized. This is the similar type of magnetization as we have in the magnets that we use and buy for everyday purposes. So where the crust and the rocks are magnetized. And with these satellites, then we are also able to make maps of the crust. And you see these very strange patterns between strong magnetization and weaker magnetization, which then, of course, reflects the history of the geology in the region and so on, and the type of rocks and stuff like this. So this is an interesting aspect, and the better the instruments, the more precise and the higher resolution information that we get. I think I will skip explaining this. This is a cartoon. I will probably share the slides with this one, but what it actually tries to say is that because the liquid seawater, ocean water, is salty, it is conductive, and when that seawater is moving in the presence of the main magnetic field of the Earth, that creates an additional magnetic field. And we can actually measure that. We can measure the magnetic field of the seawater, ocean water, and how it is moving. And therefore, we can also somehow estimate how much water is moving all around in the ocean simply by its magnetic signal. This is a tiny signal, and you know, very hard to detect. But if your instrument is good and your modeling is good, then you're able to distill it and to decipher it. And this is exactly what we have been able to do with this mission. Now, my very final example is this one. This is again in space physics, coming from SWARM. I do not know if you have heard about this. Some people have, some people have not. But we have discovered with this mission and through the help of what I would call citizen scientists, community scientists, a new phenomena, it's not exactly an aurora, but it is an optical phenomenon in the sky, which was characterized by very, very strong temperature variation. So it's very hot gas that is moving very fast in east-west direction, in narrow band, typically 20 to 30 kilometers wide, and they are very long, several hundreds, if not thousands of kilometers. And these were discovered by a Facebook group called the Alberta Aurora Watchers in Canada, who were up at night looking at pictures, and they were trying to take pictures of auroras in the sky and sharing them between themselves. And they discovered all of this. And they tried to understand what it is, and they, at some point, they decided to call one of the scientists who was working on this mission called Swarm. And they... Okay, thank you. I'm about to wrap up here. And they then they said, well, what kind of aurora is this? The fact is that by looking at where these pictures were taken and when they occur, it was found out it was not auroras because they were occurring much more to the south. So they're to the south of the auroras, and nobody really knew what it was. So this sparked off a very strong debate among scientists about what it actually is. And in awaiting, sort of trying to find out what it is, these aurora watchers, they needed a name for it because they took pictures of it whenever they managed to. And then they, one guy, he referred to this movie called Over the Hedge, where the animals, when they met somebody that they did not know who it was and what kind of animal it was, they decided to call him Steve. And these aurora watchers, they actually decided to call this phenomenon Steve because they did not know what it was. But it turned out to be not such a bad name because it is actually a strong thermal emission of gas, which is causing an enhancement in the velocity of the motion of the particles. So the acronym STEVE now has also become a scientific term, and the Aurora watchers in Alberta, in Canada, they have also joined what is called the Aurorasaurus project, which is, and everybody can actually join this, which is on internet and live on Twitter, where you can give feeds on the detection of all of these things based on what they see in the sky when they take the pictures and so forth. So you can read more about Steve in this Wikipedia link that I show at the bottom of the page. But the bottom line here is that for teachers and for youngsters and for everybody actually, who is not even an expert, there is things that we can do in order to actually help advance the understanding of space physics and of magnetism, because this information that is being collected here, not only about this beautiful optical phenomena in the sky, but also about where the auroras are and what they look like and how their features are, how they move on the sky and so on, is being used by scientists, and there's a value, a scientific value as well. So with that, and a picture of waves in the magnetosphere, which is another aspect that I didn't want to go into detail about, I'd like to thank you for your attention. Thank you very much.